Hello, everyone. Welcome to lecture 22 on finite element method. Again, we start with a short overview of what we have done before. We had talked about the big map or the roadmap of the finite element method, and we mentioned that this map for a two-dimensional finite element method is very similar to the same thing that we did for a one-dimensional finite element method. We talked about different approximations, and then we had a more detailed map when we were talking about the one-dimensional FEM. And then we had this sort of wrap up and overview of 1D FEM. The important thing for you is that you start from a strong form, that's a second order differential equation. You multiply that by test functions, you integrate, you impose your boundary conditions, then you go through these mathematical steps, and then you end up with this thing that is basically your stiffness matrix. It's K. Now, the next step is to bring that K from a physical space to natural space and do the integration using Gauss quadrature. All right, now, when we want to do the same thing in two-dimensional finite element method, basically we go through the same order, the same map, except that now we need to have some additional mathematical preliminaries that we discussed. So we introduced this sort of index notation and this Einstein summation convention. We introduced the double dot product and also the Kronecker delta that we will also use in this lecture in particular. And then we also said that now using this index notation, you can write the material response, the Hooke's law, in a very nice compact form using basically the summation convention that we introduced earlier. And also we mentioned that now that we are familiar with this sort of vectorial or tensorial operations, we can extend our classical derivations to, let's say, more advanced versions of them, which would be gradient, divergence, and curl. And then we defined these operators for particular scalar, vector, and tensorial field or matrix field if you want. And then we also mentioned that if you want to think of the big picture of mechanics, whether it's a mechanical problem or a thermal problem, it's very similar. And the important thing for you, the take-home message from all this discussion, was that the strong form, the governing equations that we had to start with, it's now for mechanical and thermal problem very similar. It's basically the divergence of that flux. Now, if it's a thermal problem, that flux would be heat flux. If it's a mechanical problem, that flux is something like a momentum flux or force flux, if you want, which is similar to stress, if you want. So that's sort of the understanding of what stress means. And then this would be now our starting point for a two-dimensional analysis. So we did this step to come to our strong form. And then we learned that if you want to do approximations, we can use shape functions for a two-dimensional analysis, and based on that, we introduce different elements and their shape functions too. Also, we introduce our Gauss quadrature for a two-dimensional problem, whether it is a triangular element or whether it's a quadrilateral element. Okay, so now we come back to this point, to our map, and as we discussed, we have done this now. So we have gone from, we have done in a 2D version, we have learned how to do this approximate form. We haven't done this. We know what is the strong form. So what we wanted to do next is to go from a strong form to weak form, which we did in the last lecture. And now what we want to do today is basically to come to this part and basically cover the rest of this map, okay? So just a very short overview of how we came from strong form to weak form and to approximate form. Basically, this was the problem. You would say you have a two-dimensional problem. Now you have your strong form, which is the differential equation subject to boundary conditions. These are Neumann type and Dirichlet type boundary conditions as we discussed before. And then we go through the same game, basically. You multiply by a test function and you integrate over the domain. Then you use this divergence theorem and you go through mathematical steps and you end up with a weak form. So this was our weak form. And then the next thing we want to do is to go from weak form to approximate form. And in order to do that, again, we introduce these shape functions into our test function and into our displacement function, basically. And by doing that, we go through the mathematical steps again, similar, very similar to what we have done in the finite, in the one-dimensional version of this, and we come to this picture. We come again to this stiffness-like structure. So we would have this integral that we can identify as being some sort of stiffness, and if we take that out, you would basically have something which would look like this. So you would have your stiffness components multiplied by displacement components, and these connections between the components of each nodes and their corresponding displacement. We also discussed that, and eventually the message is that for instance, for a triangular element, you can repeat this process for each row, and then eventually you would expect to have a 6x6 stiffness matrix for that element. And also we came to this slide, basically. So this is what we discussed in the previous lecture. All right, so this is our weak form, basically. And now this is kind of our approximate form. But this approximate form, it's not exactly the familiar form you want. This is the form that we wanted. So basically, it's the same thing. Okay, so this is exactly our Ku times F for one single element, and then each component of that stiffness matrix is defined as such. So before I go further, what we want to understand is what is this. So we want to understand the, let's say, the physical meaning of that. So again, the definition is exactly the same definition as we had before, and we will work on this. We will simplify this, and we will make it more suitable for a computational implementation. But the important thing is that we want to understand what is the meaning of this. So if we say K I J A C, what do we mean by that? Obviously, this means the stiffness between nodes I and J and for directions A and C respectively. Okay, what does that mean really? So this is what you can, or this is how you should read this. So this is the stiffness between nodes I and J and between the directions A and C. But we need to have a physical interpretation of that, and that's what we want to do. So in order to do that, I need to bring us back to our one-dimensional example. So let's think of our one-dimensional example that we always had. So let's say this was our simple truss element that we also mentioned. You can replace it with a spring with, let's say, a stiffness K. And if this was node 1 and this is node 2, and also imagine this is a one-dimensional problem. The stiffness of this thing was, the stiffness matrix of this element was K minus K minus k. Okay, so this was the way that the stiffness of this was defined. Now, let's, instead of writing it, let's write it with its components. So this would be basically K11, K12, K21, K22. Okay, and then again, we use exactly the same convention that we did before. Superscripts means that they are nodes. Okay, so superscripts are nodes, subscripts are directions. This is exactly the same thing that we did before. So what is the meaning of K11? In other words, let's just for the fun of it, okay, let's think of K12. If you think of K12 in this example, so the example is now very simple, right? I mean, we want to just think of this one-dimensional problem. So I'm asking you, what is the meaning of K11? Let's go backwards a bit. So if we think what is the meaning of K12, you may say this is the stiffness between nodes 1 and 2. Okay, that's all right. That's a good explanation of what it is. But again, the physical concept is still kind of missing. So if we have two nodes, then we know, okay, you have a stiffness between them, which funny enough, now you have a minus sign, but that is not a problem for us. But if you want to just use that analogy, okay, let's say you want to explain it in words, it would be a bit strange to say that this is the stiffness between node 1 and 1, right? I hope you see what the problem is basically. So K11 is indeed the stiffness between node 1 and 1. Node 1 and node 1. Okay, which is a little strange. So the reason it's strange is because we should re-understand, we should relearn what the stiffness means. Okay, so your understanding of stiffness as just a spring constant is no longer a deep enough understanding of it. We need to go one step deeper to understand what this means. And in order to do that, I complete this system for you, and then you could immediately see what is happening. So if I say this is K11, K12, K21, K22, and now we write the system together with the displacements. So this would be U1, this is U2, and then F1, F2. All right. So if you think about this, now you see K11 is multiplied by U1, K12 is multiplied by U2. Now that K11 that is multiplied by U1, it contributes to F1. Okay. The K12 that is multiplied by U2, that also contributes to F1. Okay, so a better way of understanding this, or a better way of explaining what the stiffness ij is the following. And let's see if now it makes sense to you. And then basically using this understanding, you can explain this and everything that we do also in 2D. So Kij is basically the ratio of stiffness, the ratio of the force at node I with respect to the change of displacement at node J. So this is basically a change of force at node I divided by, I'm saying change because instead of delta, okay, so this would be delta Fi, obviously, divided by, let's say, change of displacement at node J. Okay, so basically it tells you if you change the node J a little bit, so let's say I move this U2 a little bit to the right, or sorry, if I change it, it's a vertical, sorry. The direction doesn't matter. If you change this just a little, the question is, if you change this a little, how much you need to change the force at F1 to make that happen, to make that equilibrium, basically. Okay, so this is the condition, which obviously, again, it's in a more mathematical way. Maybe you can just say it's delta F J, roughly speaking, divided by delta UI. Okay, so this is the way to understand it. And then if you understand it like this, then this 1,1 has no problem. Basically, it is not the stiff, well, it's the stiffness between node 1 and 1, but it's not a problem that you have this 1 and 1. Because the second time that you say 1, you are actually talking about the force at node 1. The first time that you talk about 1, you are talking about displacement at node 1. Okay, so it's okay to understand it like that. All right. So this is very important to sort of have this interpretation of the stiffness, because now with this we can come back to our previous slide here, and we can.
Actually, can I say something?
Yes, please.
You wrote delta Fj, but isn't it delta Fi and delta Uj?
Yes. Thank you very much. So this is the denominator is I, denominator is J. Thank you. All right. So now with this, we can also go back and interpret this one, which is slightly more complicated, but actually now that you look at it, it makes perfect sense. So this is basically the stiffness between nodes I and J, or between direction A of node I and direction C of node J. Okay, so let's say it's a stiffness between direction A of node I and direction C of node J. Okay, so from that perspective, again, if you want to also sort of connect it to the concept of force, it's the same thing. You want to know how much the force of node I at direction A is changing if you move the direction C of displacement of node J. Okay, so basically this is again. Now I intentionally write it like this. So again, you should not get confused if you don't have these brackets. I mean, naturally, the first component corresponds to the first node, and the first direction, sorry, the second direction C corresponds to the second node. So this would be, again, very similar to what we did before. This is the delta or change of force at node I in direction A divided by change of displacement at node J in direction C. All right. So this is very important that you sort of grasp this. You should feel this, because when you need to assemble these elements and calculate their stiffnesses, it gets slightly more complicated. All right. So we are done with that. So we know now what this thing means. Okay, the concept of it is important. We still need to calculate it, and that is what we are going to do next. But at least you know the concept. Do you have any question? All right, so now if you think of a triangular element, for instance, that thing that we just discussed, it happens several times. So let's identify this thing. So the I and J, these are the node numbers, right? A and C, these are the directions. So that means I and J, they go from 1 to node per element. So if you have a triangular element with 3 nodes, then your I and J could be 1, 2, and 3. And then A and C, these are the directions. So these are basically, in a 2-dimensional problem, these are either X or Y, which means they are either 1 or 2. So from that perspective, now if you think of a triangular element, you can think that well, let's say for a linear triangular element, you would have 3 nodes. Okay, so this is the 3-noded element. Obviously, if you had a 6-noded element, then it would be 6 nodes. So for a 3-noded triangular elements, you have 3 nodes, 1, 2, 3. And now you can assign a direction or 2 directions per node, basically. And you would have directions 1, 2, 3, 4, 5, and 6. These are the degrees, basically, all the degrees of this element. Okay, so basically that means that the stiffness of the element, it is constructed from these boxes. You see, on these boxes now, I'm just writing 1, 1 here. 1, 1 is only about the nodes, okay? And then you should, and then similar to before, you shouldn't be surprised that it is 1, 1. Okay, we just learned that these 2 superscripts, they have different meanings. So if they have the same number, it's not a problem. So each of these, so if you think of the stiffness 1, 1, similar to this, if I and J, they are both 1, that means delta F1, but in any direction, divided by delta U1, also in any direction. So if you think of it that way, for instance, again, about K11, you can think of it as being delta F at node 1 divided by delta U at node 1. All right. So, and now you can clearly see that the force at node 1, it has 2 directions. It's the vector. The displacement at node 1 is also it also has 2 directions. So it's a vector. So for each of these components, you would have one particular component to that box. So basically that Kij or K11 itself, it has 4 components. Okay, in XX direction, XY direction, YX direction, and YY direction. In other words, if you kind of do this for each of these, so 1, 1, 1, 2, 1, 3, 2, 2, 2, 1, sorry, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3, you can write each of these boxes, and if you can appreciate the colors are corresponding in the 2 pictures. So each of these is now a 2 by 2 box. Okay, so the stiffness of that triangular element, it looks like a 3 by 3 box because you have 3 nodes, but then for each node you have 2 degrees, so you get 6 by 6 as the dimension of your stiffness matrix. Does that make sense? All right, so now that we do this, again, remember the whole thing that we do is the key purpose, the ultimate purpose is to understand this so that we can later implement this. Okay, so this is nice, of course, to talk about this as being just as having 2 different superscripts and then 2 different subscripts, right? So this is okay as long as I want to write it. So it's good when you write it on a paper, but if you want to implement this, you cannot really nicely implement superscripts and subscripts separately, right? So you need to give them individual numbers, and that is where these degrees come to the play, right? So then you would say, well, now if I want to identify these rows and columns, again, these are the rows because of the forces. So these are how the force would correspond to the rows of the stiffness, and these are basically corresponding to the displacements that they are going to be multiplied with. But then in this case, for instance, you have 6 components in each direction, and then these are exactly 1x, 1y, 2x, 2y, 3x, 3y in each direction, basically. Okay, now we know these degrees. We know what is the number of 1x, or we know what is the number of 2y. 2y, it has the number 4. Okay, so we use this property and we write these based on the numbering. Yeah, based on this numbering, and then you would see basically this one. Okay, now in this picture you have a usual stiffness matrix as you would have always before. Then you don't have to worry about the superscripts or subscripts or the dimension of the problem. Now it's a matrix. It's a 6 by 6 matrix. Okay, and then you just construct this as at each element. Okay, now obviously you remember once you have this for each element, you still need to assemble different elements together. Okay, so that is the next step that you would have to do, like you always do. But that assembly process, similar to what you had done before, the assembly process itself, it happens when you assign these degrees and these numberings. It happens somewhere else in your code. That's not a problem. So the key difficulty, or let's say the part that you need to be careful about is to have these elements. So if you, for instance, let me see if I can, let's say you have this one. So this is for the element that you see. Now think about this case that you have another element just attached to this. And let's remember these degrees. So I'm putting them down here. Okay, now let's think of this, that we have a second triangle. Actually, yeah, I can draw it like this. So let's say you have this second triangle. So that was your first triangle. And now this is the second one. So on this second one, you see now you have 4 nodes in your whole structure. On this one, now the degrees you would have are, for instance, 7 and 8. All right. So now, also for this triangle, you can write its stiffness. The stiffness of that, it's also a 6 by 6 matrix. So the degrees would be 1, 2. Let's imagine that here you went in a counterclockwise. So this was 1, 2, 3, 4, 5, 6. So let's say we do the same thing here, starting from the same point. The degrees that you have would be 1, 2, 5, 6, 7, 8. 1, 2, 5, 6, 7, 8. Okay, and then you would have obviously the components corresponding to that, but eventually this is just a 6 by 6 matrix. Okay, so when you need to assemble these, you would do exactly what you did before. So for instance, this box that is on 1, 2 would be assembled with this box here. You would add them together, so they are corresponding to the same degrees in your global system. Okay, so what I'm trying to say is that as soon as you understand how the stiffness for one element works, then you are done. You have nothing more to do compared to what you had done already for a one-dimensional FEM or for a truss structure. The assembly process is exactly the same assembly, the same subroutine in your code. Okay, so basically the remaining part is assembly, and we are not going to really discuss it because you know how the assembly part is done. Okay, so the key question is just one element stiffness. So the question is element stiffness, not the assembly part of it. All right, so we discussed enough about a linear triangle, but also if you have a different element, if you have a rectangular element or linear quadrilateral element, bilinear basically, you have a similar game to play. So if you write the stiffness of that in terms of these blocks, basically, you would have a 4 by 4 block stiffness, but then each block is a 2 by 2 matrix by itself. So it is now again 8 by 8 in this case too. So if you play this game for all kinds of elements, you come up with the same answer basically. So if it's a linear triangle, you would have 6 by 6. If you have a quadratic triangle, that would be 12 by 12. For a bilinear quadrilateral, that is 8 by 8. For serendipity biquadratic quadrilateral is 16 by 16. And for Lagrange quadratic quadrilateral is 18 by 18. Okay, but in any case, this is now, I hope this is now completely understood. So you know exactly how to do this part. The only remaining thing is this. Okay, so if we just figure out how to do that, then we know everything that we need to know. All right. Okay, so here let's see what are the problems. We have a few problems here. If you want to calculate this, so if I just ask you what is this thing, you don't know yet. There are a few problems. One is that there is an integral. So we don't like integrals, obviously. But we know that later we want to change this to a summation over Gauss points. Okay. So that is not a big problem. We know at some point we can use Gauss quadrature. So the integral, we kind of know how to handle that. But then there are still two problems. One is, what are these guys? So these are the derivatives of shape functions. Now, these are the derivatives in a physical space, okay? which tells you eventually what you have here is a function of X. It's a function of your physical space, right? So this is not suitable for integration. Okay, so that is problem number 2. So problem number 1 is there is an integral. So let me just maybe identify the problems so that we can solve them one by one. So there are 3 problems with this. One is that it is an integral. And then the answer to that is, okay, we need to go to Gauss quadrature. Another problem that we have is that the whole thing is a function of X. But if you want to use Gauss quadrature, you need it to be in terms of the natural space C. So we have that additional problem. Now, the answer to this is basically transformation of X to C. Okay, so we need to make this mapping between the physical space and natural space. The third problem, which is the most obvious one, is what is that E? Okay, so what is this? I mean, we keep writing it as just a constitutive tensor, as a fourth order tensor. So what is that? Now, this is nothing that you don't know already. Maybe you don't know it in the way that I am going to write it in the next slide. But this is exactly what it is. Okay, so if you have your elastic material properties, you can exactly write your constitutive tensor. You can write your E. All right. So in this example, by the way, I'm using this E for the constitutive tensor, and I'm using also E here. Don't get confused. The one with subscripts, obviously, this is your constitutive tensor, and the other one is just the usual Young's modulus. Constitutive tensor. And as I mentioned, this is a fourth order tensor in principle, which means each of its indices in 2D, they can go from 1 to 2. So it would be 2 by 2 by 2 by 2, which tells you it has 16 components overall. All right. So this is the constitutive tensor, and then a nu here. This is a nu, and that's Poisson ratio. Again, in Greek, it would be basically like this. It's mu, and then E is just the elastic modulus. Or Young's modulus. All right. Now, delta is Kronecker delta. In this picture, also delta is Kronecker delta, and we introduced that before. Let's do an example together. So for instance, I will ask you, what is E111? E1111, so 4 times 1. We want to calculate that. And by the way, also remember, B is repeated twice, so that means a summation over B. and D is repeated twice, that also means it's a summation over D. Okay, so we have these two summations. All right, so we need to calculate these 16 components that I just mentioned. Let's calculate a few of them together and learn how this thing is done. All right, so what is E1111? E1111. What's that? This means A is 1, B is 1, C is 1, and D is 1. Okay. By the way, in your code, basically this means you have 4 loops over A, B, C, and D, and you just calculate it within the code in no time, right? So let's calculate each of these terms. So this is the coefficient of that term, 2, 1 plus nu. Now, what is delta AD? If A is 1 and D is 1, delta AD is 1 because A and D are equal. Delta BC is also 1 because B and C are also equal. So that is 1 times 1. Plus, now delta AC and BD have a similar story. A and C, they are both 1. B and D, they are both 1. So you also get 1 times 1. And then you have the other one. So you have plus E nu divided by 1 minus nu squared. Now, delta AB and delta CD, they are also both 1. So you would have, again, 1 times 1. All right? So if you want that, then basically you have a 2 here that is canceled with a 2 in the denominator. Okay, this is just a 1. So you can add them up together like this. So this would be 1 minus nu squared in the denominator. Then this would be E times 1 minus nu plus E nu. Right? And as you can see, you would immediately come to E divided by 1 minus nu squared. All right. I hope I haven't made a mistake, but this is basically that. Now, the important thing here is that we are talking about a particular version of a 2-dimensional problem. So remember we said 2-dimensional problems could be plane strain and plane stress. What I am writing here, what I have written here is the plane strain version. Okay, what does that mean? Basically, that means for you that the Poisson ratio in this relation can go from, well, it can go maximum to 1. So incompressibility is 1. Usually Poisson ratio goes to 1/2, but in a plane strain case, because it has this degenerated definition, it's a fictitious definition basically. So this is not the real Poisson ratio of the material. The 3D Poisson ratio is maximum 0.5. So basically here, the Poisson ratio that you have, we just write it with different color, yeah, maybe this, nu is the usual nu, the 3-dimensional nu that you have, divided by 1 minus 3-dimensional nu. Okay. So basically, if the real Poisson ratio of the material is 0.5, then the Poisson ratio that you insert that you enter into this formulation is just 1, okay, to get the equivalent version, right? That's why in the denominator you see this. Otherwise, usually you would see something which looks like 1 minus 2 nu or something like that. But we don't see that because, again, we are talking about a plain string version. Nothing wrong with this. I find plain string more tangible, more let's say, more straightforward to explain. And also, when we discussed our model previously, we discussed that we have, let's say, a flat layer that is constrained for the deformation in the third direction. I think that is a nice explanation. But eventually, this thing that we have here, it doesn't matter if it's plane strain or plane stress. This definition would change if you had a plane stress problem, but the rest is exactly the same. So you don't have to worry about it. If you have a code, you would just change one line in your code. The rest is valid. Okay, so the next thing we want to do
Can I ask something?
Yes, please.
I don't understand why delta is 1 when the directions are equal.
This is the definition of Kronecker delta. So Kronecker delta, it was this thing that we defined, I think, in the mathematical preliminaries, somewhere here. Yeah, here. So Kronecker delta is basically the definition. It's like a dot product. Delta ij is ei dot ej. Okay, so delta 1 1 is e1 dot e1, which is 1. If 1 and 1 are not the same, it's 0. Does that make sense?
Okay, thank you.
Yeah, it's just a way to write that constitutive tensor. You do not have to obviously memorize it or anything. All right, so I think we were here. Okay, so now we did this for 1 1 1 1. Let's do one more. We will have a few more minutes and then I give you a break. I have not forgotten the break. So let's do one more of these. Let's do 1 1 1 1 1 2. So if you want to do 1 1 1 2, then you have E divided by 2 1 plus nu. Now here you would have AD, which is 1 2. So that's delta 1 2. That is 0. Delta BC is still 1, but that's not going to help really. So it's 0 times 1. The second one, again, delta AC is 1, but delta BD is 0. And then for the other term, you would have E nu divided by 1 minus nu squared. Now, delta AB is 1, and delta CD is again 0. So this thing is nothing but just 0. So we know how to handle this one. So remember, we had 3 problems. Now we have answer to one of them. We still have 2 problems to answer, and we will do that after the break. So we will continue based on this. I have 2:27. Let's go for a 10-minute break. So we continue at 2:37 sharp. All right, so as we discussed before, now what we want to do next is to elaborate on the structure of the stiffness matrix and address the other two problems that we had. So we want to do that. Now, in order to do that, I want to remind you of exactly of what we did for a one-dimensional analysis. because I think that that is a more, let's say, again, a tangible way of explaining it. So remember, in a 1D FEM, what we did was, again, similar to 2D. You go from a strong form to weak form and to the stiffness form, but eventually your stiffness was something like this. Okay, so you had this Kij, and then you had these derivatives with respect to x with respect to the physical coordinate, and then the integration itself was also over the physical space. Okay, so this was the first step, and this is exactly what we did also in 2D, and that's where we are. Then after this, we had this other slide, which basically allowed us to go from the physical space to the natural space. Okay, and then we saw that when you do this, this guy appears, so something like J that we call Jacobian. And once you have that, then you would end up with a function, which is a function of C. It's only a function of the natural coordinate. And if you have something like that, obviously life is easier because now you can immediately integrate over the, let's say, over the natural space. So that's the question. That's what we want to do. We want to go from our physical space or the derivatives in the physical space to the derivatives in the natural space. Okay, so remember again, we had two issues left. We had this one and we had this one. The integral one is the last step, is just doing the Gauss quadrature. This is the one that we want to discuss just now. Okay, so the first issue is addressed using what is in front of you. What we want to do now is to look into those derivatives. So you would want to calculate this nix or njx. So the question here is how to calculate, for instance, nix. All right. Now, remember, first of all, when we have this derivative, this has two directions. So it's similar to a gradient. N is a scalar valued function, right? But the derivative with respect to x, it basically gives you a vector. So this thing that you are looking at is having two components. It's derivative of ni with respect to x1, which is actually your coordinate x, and then there is derivative of ni with respect to x2, which is your coordinate y. Okay, so this thing itself is a vector. That's the first thing we should not forget. But now, how can we calculate each of these? Let's look at it and then exactly play the same game that we played before. So if you say it's, for instance, derivative of ni with respect to x, imagine that you have x as a function of c. That's what we want to do, right? So if you have this, it basically means that the coordinate x would be a function of c and eta, and coordinate y is a function of c and eta. Please pay attention that here x and c, they are bold letters, and here they are not bold letters. So these are basically their components. Okay, so this is essentially the chain rule. So if you have that, and n is a function of x, but you want to express it in terms of c, so this would be derivative of ni with respect to c, derivative of c with respect to x, plus derivative of ni with respect to eta, derivative of eta with respect to x, right? Remember, ni is a function of c. Now, if c is a function of x, you can write that. And by the way, I also maybe we should write the opposite of this, or the inverse of this mapping. I mean, if you have something like this, obviously you can imagine that this also basically means that C is a function of X and Y, or eta is a function of X and Y. In other words, it also means that C is a function of X. Okay, so I mean, you may say that your physical space is a function of natural space, or you may say your natural space is a function of physical space. It's a one-to-one mapping. It depends how you want to formulate it, right? But here, because let's say we know that the ends that they appear here, they are in the physical coordinate system. I am going from the physical, okay? But then these ones are the ones that we had in our handouts basically previously, and they are the natural ones. Okay, so that is one. And then you can repeat exactly the same thing for the y direction. So that would be a derivative of ni with respect to c, derivative of c with respect to x, sorry, with respect to y, plus derivative of ni with respect to eta, derivative of eta with respect to y. Okay, so this is not too bad. Now, let's just remember. So you have this simple connection, right? Now, instead of these, I can also put it in a matrix form, in a nicer form. That's what we want to do next. So let's just do that. So this is what we want. This is the question we have. And now you have these. So let me just put this maybe here in yellow color. So now, based on what you have in yellow on the right-hand side, and then what you want to calculate here, you can clearly write the following. Sorry. Derivative of ni with respect to x, and derivative of ni with respect to y. Now, this is exactly the vector that we had. Now, what we want to do is to collect these similar coefficients into the same matrix. So basically, if I do that, I would have something which looks like derivative of c with respect to x, derivative of eta with respect to x, derivative of c with respect to y, derivative of eta with respect to y. Okay, so you construct this mapping, basically, this square matrix. And if I multiply that by the derivatives in the natural coordinate, in the natural coordinate system, then I should get what we want. Let's see. All right, so now look at it. Derivative of c with respect to x times derivative of ni with respect to c. So that's the first term here. Now, derivative of eta with respect to x, derivative of ni with respect to eta. That's the second term here. So this is derivative of ni with respect to c. Okay, and then the same thing for the second one. So basically, what I'm trying to say is that this matrix seems to be a very nice and useful matrix. Okay, so we want to look into that a little more carefully. But you get the idea. Yeah, now you know where the matrix is, or where that matrix is coming from. Okay, so it seems that I can write all of that yellow equation that we had as just, let's say, derivative of n I with respect to x, right? So this is, see, this is that vector that we just had. Okay, and remember, instead of this, we just called it nix. So this is essentially my nix. It's the derivative of shape functions with respect to x coordinate. This is now ni eta, sorry, nix. This is the derivative of shape functions with respect to c coordinates. Okay, so you have this thing. And clearly between the two, there is that nice relation. So it seems that the yellow equation that we had before, it was like nix. This is now the left-hand side. Is this matrix now in front of us? Let's not call it anything for now, but there is a matrix. Okay, there is that thing that I'm not going to call it anything, times ni c. Okay, so let's see what would be a good name for that matrix now. We want to give it a name. If I look at the components of that, you see, it's derivative of c with respect to x, derivative of eta with respect to x. Okay, so if it was the opposite of that, so if it was derivative of c with respect to x and derivative of c with respect to y, that would be a nice matrix. I mean, that would be more familiar to us. So let me just write the familiar form and see if we can connect these two together. So this is the one that we are not sure how to call it. Okay, but this is essentially this thing that is going there. Now, if you have a matrix like this, derivative of c with respect to x, derivative of c with respect to y, derivative of eta with respect to x, derivative of eta with respect to y, I don't know if you remember the way that we define the gradient operator, but this is very similar to that gradient operator definition. This would be your derivative of c with respect to x. Does that make sense? So this would be that. Or otherwise, if you wanted to define something like derivative of x with respect to c, this would be the derivative of x with respect to c, derivative of x with respect to eta, derivative of y with respect to c, derivative of y with respect to eta. Okay, so the row follows the denominator. The columns, they follow the denominator, basically, either way. Okay, so derivative of let's say if I want to give it a universal definition, it's like this: derivative of u with respect to v, if it's a matrix which has components ij, let's call that alpha beta so that we don't confuse things here. If it has a component alpha beta, it's like derivative of u alpha with respect to v beta. Okay, this is kind of the way that we define a gradient and so on. Now, if you look at this thing is exactly the derivative of x with respect to c. So this is our Jacobian, right? Okay, so this is our Jacobian. This has a name, right? Again, remember the whole game is how to call this thing. And it looks like something familiar. We don't know exactly what it is. So let's see what it is like. It's not Jacobian because Jacobian is this one. Now, this thing is the inverse of this, right? So if you multiply them, you get identity. So basically this one is Jacobian inverse, right? So this one also has a name. This is the inverse of Jacobian. Okay, so because things got a bit crowded, let me just come back to this. I will clean this up. So we have this sorry, we have this thing that we call Jacobian, and that is the derivative of x with respect to c. And by the way, remember this is exactly what we did in the 1D version, right? The j, if you remember, j was the derivative of x with respect to c. Okay, so this is not a new thing. Now, the inverse of that would be derivative of c with respect to x, which we also need. But this thing is the transpose of this. You see? These two components are in the wrong order, in the opposite order. Okay, so that thing that we want to give it a name, it actually has a name, is J minus transpose. It's the transpose of inverse of the Jacobian. Does that make sense? So this is a kind of the story here, and then all right. So that's all you have to do, and basically you don't have to worry about that anymore. It's going to be J inverse transpose times that. This is the name of that guy. Okay, and well, now we don't have to have these anymore either. All right, so this is not too bad. Remember what was the question? The question was, what is this? Now you have it exactly in terms of your natural coordinate system. All right, so in other words, what we want to do now, or the way we want to write this thing now, is using this notation that we have here. Let me just rewrite that in its extended version. Remember, Jacobian is just derivative of x with respect to c, and its inverse is simply just its inverse, and we just got this yellow equation. Okay, so using this, we can expand our green equation. Instead of this nix, now we can nicely write them in terms of what is left. So this would be simply this would be J in transpose dot NIC. The B component of that, and then your A, E, B, C, D is still there. And the next one would be the same story. So it would be J in transpose and J C component D of that DA. All right, so we have come one step further. The last thing you need to ask yourself is how to calculate that J, right? So you know how to calculate the inverse of a matrix, you know how to transpose a matrix. So then the last question really is, what is J? How to calculate the J itself. So how to do J. And this is no surprise. This is exactly what we did before. Remember, the trick is to write X as a function of Xi and eta. Or let's say Xi bold. How do you do that? You just use the shape functions. So that X is N, let's say NS XS. And now because each of these n's are a function of Xi and eta, you would naturally have your X as a function of Xi and eta, right? This is exactly what we did before too. So we push this thing up. And all you want to do now is to expand this sort of relation. So remember, J is a square matrix. It has 4 components. So I'm going to do this one by one so that you can kind of digest what is going on. So let's say J11. J11 would be the first or 1 component of the derivative of X with respect to Xi. That would be derivative of actually coordinate X with respect to Xi. Okay, so it's not bold anymore. Okay, so X1 is actually X and Xi1 is Xi. Now, see this one? That is basically the derivative with respect to Xi of, instead of X, you can write that NS XS. So XS would be just the coefficient, it comes out. So you would have XS times derivatives of NS with respect to Xi. Okay. So if I want to expand that, let me remove this guy. If you want to expand it, then you would have something which looks like this. X1 times derivative of N1 with respect to Xi plus X2 times derivative of N2 with respect to Xi plus, I mean, you go up to then, let's say X node per element times derivative of N with respect to Xi. All right. So this would be for 1 component. Now clearly you can do this again for each of the components, and that's what I'm going to do next. So let's just do this for each of the components, it's going to look like this. J11 is derivative of x with respect to c. J12 is derivative of x with respect to eta. J21 is the derivative of y with respect to c, and J22 is the derivative of y with respect to eta. Now, if you do each of these exactly like what we did before, the first one would be something which looks like this. It would be x1 derivative of n1 with respect to c plus x2 derivative of n2 with respect to c. And you play this game until node per element derivative of n node per element with respect to c. Now for the other ones, you play exactly the same game. So here, you do exactly the same thing, except that you want to calculate the derivatives with respect to eta instead of c. All right. And now for the remaining two, you also play the same game, except that now instead of x, you would have y as their components. Okay, so all you need to do is to replace these x's with y's. I hope you can kind of follow what's going on. But the nice thing about this is that, as you can see, it seems that you can also collect this, or you can write this in terms of a, let's say, in a matrix form. Okay, so if you look at the components, you see this repetition basically. So it seems that you can collect all of these in a matrix and collect all of the coefficients in another matrix, and that should also work for you. Okay, and that's exactly what we do next. So if you do that, let me just introduce a matrix to you and see if it helps. Think of a matrix like this: derivative of n1 with respect to c, for instance, then derivative of n2 with respect to c, derivative of n node per element with respect to c. So all the derivatives of n with respect to c in the first row, and all the derivatives with respect to eta in the second row. All right, so you have these. So first of all, you can see it's 2 rows and n node per element columns, right? And then we multiply these by a matrix which looks like that. It looks like x1, x2, x node per element, and then y1, y2, y node per element. Okay, So if you look at this, let's see what you get. You get derivative of n1 with respect to c times x1, derivative of n2 with respect to c times x2, and so on. So let's see if that is familiar. Derivative of n1 with respect to c times x1, derivative of n2 with respect to c times x2. So it turns out if you multiply these two, you get something which sounds like Jacobian. So you get definitely something which is first of all, it's a 2 by 2 matrix, right? Because of the dimensions, you can clearly see you are going to end up with a 2 by 2 matrix. Let's identify the components of that. So that first one up there is exactly J11 if you compare with the previous slide. Now, the next one, so this one, the first row, second column, that means the first row of this with the second column of this. That would be derivative of n1 with respect to c, y1, derivative of n2 with respect to c, y2, and so on. So if you go to the previous slide and you look at that, it's this one. So first row, second column is not J12 actually, it's J21. So you see that another, let's say another transpose is about to happen. So that would be J21, and then there, if you look at it again, this would be J12, and that would be J22. Okay, so this thing altogether is your J transpose, which is very nice because remember we actually wanted J inf transpose. So that means if you do this, you immediately get J transpose. You don't have to transpose anything. You just invert it and you get J inf transpose. All right, so this is how you would calculate your J. Now, let me just bring this slide. But by the way, obviously, another way of doing this, if you don't want to see the transpose, is the way that I am showing in the next slide. You can change the order of these, and you get the transpose version of that, right? So this would be also J. So in some books, you may see this definition or that definition, but now you see what it is. But eventually, this J is your derivative of physical coordinates with respect to the natural coordinates. This is what it is, the Jacobian. All right, so now we have everything. You have E, you have these. The only thing you don't have is the last step that we needed to discuss, and that was the integration part, right? So we have these two. The only thing we don't have is this dA. Okay, so you need to transform dA from the physical space to the natural space. Okay, now if you remember how the area is calculated or how the areas are connected to each other, you can immediately see that the determinant of all right, so you can immediately see that, for instance, dA in the physical space, so I'm putting X to indicate that's a physical space, it would be related to the determinant of J in the natural space times the equivalent area in the natural space. Okay, so how can we see this? You can You can see this by basically constructing a simple mapping between the two spaces. Okay, so I would like to, I can explain it to you, but I think it's a very, very nice exercise for you to actually figure it out. Okay, so let's leave that as an exercise. You don't have to have a very robust, let's say, mathematical proof. The mathematical proof is actually easy. It's eventually basically to construct how the area is connected. Remember, area is like a cross product of two vectors, right? And then if you do that cross product, you can immediately see where this thing is coming from. So you can think of it that way. Basically, the idea is that if you have, I don't know, if you have two vectors in the natural coordinate system, and then their area is something like this, in the physical coordinate system, maybe they are these two vectors, and the area is like this. So all you have to do is to calculate the area here, to calculate the area here. You have a mapping in between, by the way, that is your J. And you can clearly see that the area here, I don't know if you call this, maybe you call this UC, U eta, and then you call this UX, UY, UX, not a good name. Let me just call it U and V. So in the natural space, if this is U and V, these vectors, I put C as indication that it's a natural space. They have their corresponding vectors in the physical space. Now, in each space, obviously, the dx is calculated using your usual cross product. So you can just say it's ux times vx, and then in the natural space you would have the norm of, I don't know, uc cross product vx. And then if you do this, you get that determinant, okay? And this is like a two-dimensional problem. And then if you remember how you calculate a determinant, or if you have a cross product of two vectors, let's say you write the first vector here, you write the second vector here, right? And then you would have this ijk component. So obviously, if it is a two-dimensional problem, you are talking about the k component, which looks like this, right? You would say that k component of that vector would be this, let's say these two minus these two. Okay, so you kind of see where or how the determinant is coming or is connected to a cross product. Okay, so this is the idea. So basically, it's not too complicated to see that this thing is eventually your J11, J22 minus J12, J21. Okay, but this is like a mathematical proof. What I'm trying to say is that it's more interesting for you to not to look at it from a mathematical perspective. You can just try to make a mapping for yourself and see how that works. Okay, so for instance, if in the natural space, remember we always talk about our natural coordinates going from -2 to 2. So if you think of our natural coordinates for a four-noded quadrilateral, each side is going to be 2. Okay, now let's say the same element in the physical space, it has each side to be 5. Now the area of this would be 25. The area of this is 24. Okay, sorry, not 24, 4. When you construct that mapping using exactly what we had here, see, we have everything. You have your shape functions for that. You have the coordinates. You can calculate J, right? You just get that matrix. you construct that matrix, you calculate the determinant of that matrix, and you will get 25/4 for that determinant. Okay, so this is yeah, this is going to happen basically. In this case, your determinant here would be 25/4. Does that make sense? Yeah. All right. So that was everything for today. The most important thing for you is really to just look or use this slide. That's all you need for your computational implementation. Now we have answered all the questions. One last thing, once you write that function in terms of C and you do the integration, remember there is that weight factor for the Gauss integration. And if you have a triangular element, there is a factor 1, 2 in that formula. So don't forget that 1/2 if you have a triangle element. Okay, so now we know exactly how to calculate the stiffness for an element. I will calculate the stiffnesses for a few elements for you, for example, and show you how the assembly is done. But this is enough for you to start programming it. Thank you very much for your attention.